Our new unit begins with Newton's Law of Gravitation. Now, we learned about this last year, but let's review. So, if we have a particle, okay, let's just call it mass number 1, it is going to attract to any other particle, we'll call it mass number 2. This is gravity. We know they're going to pull on each other. This one's going to pull, I'm going to pull from the center, by the way. It's going to pull with some force of gravity, and so is mass number 2, force of gravity. Now these are going to pull with the same magnitude force because Newton's third law says for every action force there's an equal and opposite reaction force. So if M2 pulls on M1, then M1 has to pull on M2 same amount. But what is that amount? Well, it depends on the masses, and it depends on how far apart they are. So I also need to know the distance from the center of mass 1 to the center of mass 2. I'm going to call that distance r. Okay? Now it turns out that the magnitude of the force with which they pull on each other is going to be equal to capital G, we'll talk about that one in a second, times the mass of mass 1 times the mass of mass 2 divided by the distance between their centers squared. Okay, so it's going to depend on their masses. The more massive they are, the harder they pull on each other. It's also going to depend on how far apart they are. The further apart they are, the less hard they pull on each other. Now this G thing is there, it's called a proportionality constant, and it is always the same number. This particular proportionality constant is called the gravitational constant, and it is always equal to, get ready for a big number, this is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Okay, now I need these units over on the side. Basically, this proportionality constant is here so that the units work out. So if you try out the units in the equation, okay, let's try out the units in the equation. I want the units of force to come out. Okay, that's what I want. I want the units of force, and those are newtons. Okay, equals, G has these units, Newton meters squared per kilogram squared. And we're multiplying that by, here I've got mass is going to be a kilogram, mass is going to be a kilogram, so it's going to be kilogram times kilogram over, and then I've got r squared. R is a distance. It will be in meters, so that would end up with meters squared. So what happens is when you put all that together, the meters squared cancel out, the kilograms squared cancels both those kilograms, and all you're left with is newtons, which is what we want. Okay, if we use some other units other than newtons, meters, and kilograms, some other quantities, then we would have a different number. So this is the number with these units. If you're using other units, maybe you're using, I don't know, miles or feet or something, and slugs or foot-pounds, or I have no idea what else you'd use because we use the metric system in my class, you'd have a different constant. Okay. Now, as we said, this is for just two particles pulling on each other. But what if you had more particles? What would be the force of gravity going on in there? It'd be crazy stuff. So let's look at what if we had M1 again, and we had M2. Sorry, I made that too small. And then behind that we had like M3. Well, each pair of particles has their own gravitational interaction. So really what I've got going on are like, I've got a pair for this and this, I've got a pair for this and this, and I've got a pair for this and this. Let's just focus on what's going on with M1. What we say is that the force of gravity on M1 is the sum of the forces due to all other particles. Okay, so the way we'd write that is the force on particle 1, okay, the force on particle 1, like all of it together, net force on particle 1, would be the force on particle 1 by particle 2 plus the force on particle 1 by particle 3. I should be putting commas there, sorry. Plus, and you keep going. So if I had more particles, I would do more, basically until you run out of particles to do. Oh, those all should be vectors, by the way, because sometimes they'll be negative or positive or whatever. Okay, this is called the law of superposition, and I mean we've done it before. You said the net force on something is the force of what you get when you add up all the forces. What we're just saying now is that the total force of gravity on some particle is going to be, you have to do this over here for every single pair and then add them up. Now we can kind of extend this into our new calculus-based understanding of gravity. What if you had not a particle being attracted by other little particles, but what if you had a particle, let's see, M1 again, okay, it's being attracted by some extended object. Let's say it was some object that looked like, maybe like this. It doesn't look like a particle. It's like a big stick. I don't know why. I just chose that. Okay. So, I mean, do you just use the center of mass of this thing, or what if it's a bunch of different pieces just in a line? I don't know. We could use the center of mass, but there's another way to think about it. Let's take that piece and break it up into little tiny pieces. So instead of one big chunk, let's say we've got like this chunk and that chunk and this chunk and all these little pieces where if this whole thing was some mass, then each little tiny piece, say this little piece right there, is a little tiny piece of that mass, which in calculus, when you talk about splitting things into tiny little pieces, we talk about the little pieces as d, that little piece, okay? So if you did that, the force from that little tiny piece would be like a little tiny force, df, okay? And you'd have a little bit of df from every little tiny piece. You'd have a df from that, and they'd all be in different directions because I'd be coming from a different direction every time. So you'd have like this little piece, okay? And remember, on M, we have all the correspondings. This would be this little piece and that little piece. And if you did that for all of them, what you'd end up with is all these little forces, okay, that are coming from all these little pieces. Alrighty. And from our law of superposition up here, if we could just treat all of these little pieces as particles, then the total force of gravity on our particle number 1 would be what all the little forces from the other particles added up. So what I'm really looking at is the total force of gravity on my particle. Let's see, color. No, let's go back to orange. Okay, the total force of gravity on my particle 1, G on 1, would be add up df plus df plus df plus df. Well, when you're adding up a bunch of d stuff, that's called an integral. So what I'm really doing, I'm saying integrate, add up all the little df's. Okay, so what I should be able to do is find the total force of gravity on a particle from an extended object by breaking into little pieces of mass and then integrating them. And it does work. We're going to use that in our next video to try and figure out the gravity inside of the Earth instead of outside of the Earth. For right now, we can notice that for this object, if this had uniformly distributed mass, then the y component of this force on the pink one would cancel out the y component of the force on the violet one. So what you'd end up getting is overall, when we actually did this, we'd get a force that was like straight toward the center of this. And that's why we can usually say for an object, Force of gravity on 1. You can usually say for an object that we just pretend that all the mass exists here and we act like it does. So it's like the mass number 1 is attracted to the center of mass of the extended object. But it doesn't always work if these don't cancel out real nice, or the mass is not distributed really, really well, or all kinds of stuff, but it usually works. Okay, next we're going to talk about gravity near Earth's surface, and then we're going to talk about gravity inside of the planet.